Good morning, students. In this video, I am going to explain about magnetism. We'll discuss first the outline of today's lecture, that is introduction and the magnetic dipoles and also the origin of the magnetic moments. And next one is the basic parameters associated with the magnetism and the types of magnetic materials such as dia, para and the ferromagnetic materials. These are the topics we are going to discuss in today's lecture. First one is the introduction. So what is this magnetism and how this magnetism arises in the materials? So this magnetism is a natural or mystic force, or we can say that a physical phenomena developed in the materials is observed in the most of the materials. And here the magnetism is associated with the current carrying conductor and also the motion of the electrical charges. So the first, the natural magnet is identified from the mineral that is said to be the magnetite, and after that this magnetism phenomena is explained properly by the William Gilbert, and after that many scientists worked on this magnetism in theoretical and experimentally. Those are Oersted, Gauss and also these Frederick. These are all the scientists who worked on the magnetism to develop the many theories. Let me explain the reason behind the magnetism. So that is here magnetic field is a force which is generated due to the energy change in a volume of the space. So this magnetic field will develop due to the change in the energy in a volume of the space, and also this magnetic field is produced by an electric charge in motion, for example the current flow in a conductor, and also the orbital moment and the spin of the electrons. So we know that every current carrying conductor produces the magnetic field. Here this is a current carrying conductor or a current loop which will produces the magnetic field around it. And here this is a bar magnet having the north pole and south pole. Here the magnetic lines of force, which are the imaginary lines of force, will start from the north pole and will reached the south pole. Inside the magnet, the lines of force will start from south to north. These are the magnetic lines of force, like the loops which are traveling from the north to south. These magnetism will develop due to the mainly two reasons, that is the current flow in the conductor or in a material will produce the magnetic lines of force and develop the magnetic field, and the second reason is orbital movement and the spin of the electrons. This is the two reasons to produce the magnetic field. And what are these magnetic dipoles? Like electric dipoles, magnetic dipoles also exist. Here, every current, here the electron which is moving will act as a magnetic dipole, or we can say that will act as a small tiny magnet. Here, magnetic dipoles are found to exist in the magnetic materials, sim to the analogous to the electric dipoles. And here a magnetic dipole is a small magnet composed of the north pole and the south pole instead of the positive and the negative charges. And also within a magnetic field, the force of field exerts a torque that tends to orient the dipoles with the field. Here from this diagram we can understand this. Here a bar magnet is kept in the external magnetic field, then the external magnetic field applies the torque on this magnet. So that torque will tries to align this magnet into the direction of the field. So that force experienced by the magnet is is said to be the magnetic field, the measure of the ability of a dipole to rotate itself and come into the alignment of the magnetic field is said to be the magnetic dipole moment. So due to that force applied by the external field, this dipole will come into the direction of the external field. That ability of the dipole to rotate itself and come into the alignment of the magnetic field is said to be the dipole moment, same as the electric field. Here the electric field force is applied on a positive and negative charge and will try to align this into the direction of the field. This force is said to be the force experienced by the dipole in the external magnetic field to try to tends to align into the magnetic field is said to be the dipole moment. Here, what is the reason behind these magnetic moments? So I already told the magnetic moment is the basic reason to produce the magnetic field. The origin for the magnetic moment is mainly the motion of the electrons. So the electron motion is the main responsible for the magnetism in the materials. That is, we can observe that there are the two types of motion of the electrons around the nucleus. That is orbital motion around the nucleus and also the spin motion around the nucleus. Here, each electron in an atom has magnetic moments that originate from the two sources. So as I already told, every moving electron will act as a small magnet having the magnetic moment along its own axis. So that magnetic moment of the electron will arise from the two sources. That is, first one is the orbital motion around the nucleus, and the second one is the spin motion around the spin of the electrons. So here the orbital motion can be observed from here. This orbital motion is nothing but the electron moves around the nucleus in a particular axis. So due to that, the magnetic moment, the magnetism will develop along its axis. So electron is considered to be a small current loop generating a very small magnetic field having a magnetic moment along its axis of rotation. Here from this diagram we can understand that electron is revolving around the nucleus and the magnetic moment will develop along its rotating axis, and this is a small magnetic field which will produce the magnetic moment. The sum of all the magnetic moments will give us the net magnetic moment. This is about the orbital motion around the nucleus. So this will produce the orbital magnetic moment of the electrons. In the same way, the electron makes the spin moment. Means it will rotate itself, and it also rotates around the nucleus, same as the movement of the earth around the sun. So we'll discuss about the spin of electrons. When the electrons are revolving around itself, so it will produce the magnetic moment along the spin axis. So that is said to be the spin magnetic moment of the electrons. Spin magnetic moment may be a parallel or anti-parallel. So this here from the second diagram we can understand that electron will make the rotation itself around the nucleus, and also it will make the rotation itself. That spin moment will produce magnetic moment along this axis. So the sum of the net magnetic moments will give us the sum of all the magnetic moments to produce the uh, final magnetic moment. So as I already discussed, so here the magnetic moment arises due to the orbital and the spin motion of the electrons. Due to that, the magnetic field will create in the materials. But magnetism in a material arises due to the alignment of the magnetic moments. As I already told, the alignment of the magnetic moments will give us the net magnetic moment, which will give us the magnetism or magnetic field in the materials. Here, the as we already know, every material is having atoms, nucleus, and the electrons which are revolving around the nucleus. So every material has a orbital and the spinning electrons. So then all the materials can be acted as a magnet? No. So all the materials are not the magnets. So there are the two reasons due to produce the magnetism and to cancel the magnetism. Those are the first reason is Pauli exclusion principle. You might have heard about this. That is, two electrons with same energy level must have the opposite spins. Thus, so are their magnetic moments which cancel out each other. So the two electrons with the same energy levels, so as we already know, must have the opposite spins which will cancel out each other, and the net magnetic moment becomes zero. So this is due to the cancellation of the magnetic moment, the total net magnetic moment becomes zero. Then that material will not act as a magnet. And the second reason is orbital moment of electrons also cancel out each other. Thus, no net magnetic moments if there is no unpaired electrons. So orbital moment of electrons, that is orbital magnetic moments, also will cancel out each other due to the paired electrons. If the unpaired electrons are present in the material, then there exists the finite orbital moment and there is a magnetism. So here this is the second reason. Some elements such as transition elements, lanthanides, and also the actinides have a net magnetic moments, since some of their energy levels have an unpaired electrons. As I already told, existence of unpaired electrons is the main reason for the net magnetic moment. Here some of the elements, transition elements, lanthanides and actinides have the net magnetic moment due to the presence of the unpaired electrons. Means uncancellation of the magnetic moments produces the net magnetic moment. As I already told, Orbital motion of the electron around the nucleus will produce the orbital magnetic moment, and the spin motion of the electron will produce the spin magnetic moment. So we'll discuss the few equations, that is consider an electron moving in a circular orbit of radius r and with a constant velocity v and the angular velocity omega. So imagine that an electron is moving in a circular orbit of radius r and with a constant velocity v and the angular velocity omega, and we know that moving charges will produce the electricity, that is current produced due to the moment of the electron can be written as E upon T, time period, that can be written as 2 pi upon omega. The total equation becomes I is equal to E omega upon 2 pi. And the magnetic moment, or we can say that the orbital magnetic moment mu m is equal to, which is revolving around the nucleus in a circular orbit, so that can be written as total moment, orbital magnetic moment, that is can be written as the product of current into area of the loop, that can be written as the above equation, substituting in the above equation, that is minus E omega upon 2 pi into area of the loop is pi r square. So here from the above equation we can write like this: E upon 2m into L. L is the orbital angular momentum. L is equal to mr omega square, and substituting all in the above equation we will get the magnetic orbital magnetic moment equation as Eh upon 4 pi m. E is the charge of electron, H is the Planck's constant, m is the mass. Here this can be written as Bohr magneton, which is a small parameter, that is a small orbital magnetic moment, that is the least magnetic moment of the electrons. And next one is the spin magnetic moment. In the above equation we will substitute the spin quantum number, that is plus half or minus half, then we will get the spin magnetic moment, which is represented with the mu s, that is equal to 1 upon 2 into Eh upon 4 pi m. So here mu s is equal to g into Eh upon 4 pi m into ms, which represents the spin quantum number, where g is called the spectroscopic splitting factor. And the basic definitions. Next, we are going to discuss about the basic definitions. The first one is the magnetic field strength, represented with capital H. So it is also said to be the externally applied field or field strength. So it is a externally applied magnetic field which represents H, can it depends on number of turns. For example, if you take a solenoid like this, the magnetic field, externally applied magnetic field, will depends on the number of turns and current and I flowing in the solenoid, and also the length of the solenoid. For example, if the current is large and the number of turns is large, the externally applied magnetic field is also becomes increases. For the same length, if the length is increased, then the for the same number of turns and the current, the magnetic field strength will be decreased. And this magnetic field strength in general, we can understand this definition of the field strength H like this: if you kept a north pole, uh, unit north pole in a magnetic field, then the force experienced by the this unit north pole at any point in the field is said to be the strength of the magnetic field, represented with H. Means the force experienced by the a single pole in a magnetic field is said to be the magnetic field strength H, having the unit of ampere per meter. For in case of solenoid, it depends on number of turns, current, and the length of the solenoid. And next one is the magnetic induction or flux density. So represents the magnitude of the internal field strength within a substance that is subjected to an H field. So if you are applying the magnetic field externally, then how many number of lines, means the imaginary lines of force which is produced due to the external field strength is developed in a material that is represented with the magnetic induction, or we can say the density of the magnetic lines of force, density of the magnetic flux, represented with B. It is defined as the number of hypothetical induction lines passing normally through a unit area. It is measured as having the unit of Tesla or Weber per meter square. So as I already told, this magnetic induction will directly depends on the magnetic strength, If the magnetic strength is high, the number of lines of force will passing through the material normally will also increase. So we can write like this: the magnetic field strength and the flux density are both are related, directly related. So we can write B is directly proportional to the H. So in place of the proportionality, we can keep a proportionality constant that is represented with the mu, which is nothing but the permeability of the medium, that our permeability of the material, that is B is equal to mu into H. Permeability is nothing but the of the medium through which the magnetic lines of force, the ability of the material to allow the magnetic lines of force is said to be the permeability. So here mu naught is the, in case of the free space, that is represented with what? That is mu naught is equal to the permeability of the free space, and mu is equal to the permeability of the medium through which the H field passes and in which the B is measured. As I already told, externally applied field is there, and the flux density is represented with B and measured with B, which is having the medium having the permeability of the mu. And next one is the intensity of the magnetization. So this is the ratio of the M and V. It measures the degree of magnetization. If you are applying the externally magnetic field and the degree of the magnetization achieved by the materials, it measures the degree of magnetization of a material magnetized specimen and is defined as the magnetic moment per unit volume. How the material is responding to the externally applied field and the magnetization measurement observed can be using the intensity of magnetization represented with I, that is the ratio of the magnetic moment per unit volume in the particular specimen. It is having the unit of ampere per meter. And the next parameter and important parameter is magnetic susceptibility, which is represented with psi, or we can pronounce as kappa also. The magnetic susceptibility is defined as the ratio of intensity of magnetization to the magnetic field strength. Sorry, here the magnetic field strength H. So we know that if the externally magnetic field is high, the intensity of magnetization is also high. So both are directly proportional, directly related to each other. That is, H is directly related to I. So the magnetic susceptibility can be written as ratio of I and H. And next one is the relative permeability. It is a ratio of the permeability of the medium to the permeability of the free space. Higher value of the relative permeability indicates the ease with which a magnetic field can be induced in the presence of a external field H. So higher value of relative permeability represents the how the magnetic material is responding to the external magnetic field H. And with the application of the magnetic field, the magnetic moment in a material tend to align and thus increases the magnitude of the field strength. So this increase is given by the parameter is called the magnetization, such that we can write the equation like this: B is equal to mu naught into H plus mu naught into M. So we already discussed about the H, that is the magnetic field strength, and magnetic flux density B. So we can understand the relation between these two parameters like this. When a material is kept in a magnetic field, two types of induction arises, one due to the magnetizing field H and other due to the magnetization M of the material itself. So the magnetic induction B produced inside the material is given by. So if a material is kept in a magnetic field, we can observe that the two types of induction, that is due to the external field and due to the internally magnetization M. So total induction is the sum of the H and M. We can write in a directly proportionality constant, that is a permeability in case of free space, that is B is equal to mu naught into H plus M. And the above equation, mu naught is nothing but the permeability of the free space and its value is 4 pi into 10 to the power of minus 7 Henry per meters. And the above equation changes as by taking the H as common, that is B is equal to mu naught into 1 plus M upon H into H. So M upon H is nothing but a susceptibility here represented with this kappa, 1 mu naught into 1 plus psi into H. Here this mu naught into 1 plus I can be written as B is equal to mu into H. This is the relation between the B and H, which is the represents the permeability of the medium, that is B upon H. And we can, in the same way, we can understand the relation between the relative permeability and the susceptibility. So from the previous slide, I am taking this B is equal to mu naught into 1 plus susceptibility into magnetic field strength H. So I'm taking that equation, and I am taking the final equation also, B is equal to mu into H, and substitute in the mu is equal to mu naught into 1 plus susceptibility, and here mu upon mu naught is taken to the left hand side, then we can write it that ratio as the relative permeability, that is mu r is equal to 1 plus susceptibility psi. This is the relation between the susceptibility and the relative permeability. And the last one is the Bohr magneton. So this Bohr magneton is the elementary electron magnetic moment, and no electron can have the magnetic moment less than the Bohr magneton. So this is a like unit, is a fundamental value of the magnetic moment of the electron, which is a lowest value of the electron magnetic moment. Less than that, there is no magnetic moment of the material, which is the ratio of EH upon 4 pi m. It is a natural unit for the measurement of the magnetic moments of the electrons and the atoms. It has a value. That value is 9.28 into 10 power minus 24 ampere square meter. So those are the definitions about the parameters in the magnetism. The definitions are magnetic field strength H and the magnetic induction B, intensity of magnetization I, and the relations between the susceptibility, permeability, and the magnetic induction and H, field strength H. And let us discuss about the types of the magnetisms, that is said to be the how the magnetism changes depends in the different materials. So here depends on the existence of the alignments of magnetic moments. As I already told, the basic reason behind the magnetism is the movement of the electrons and the presence of the magnetic moments. Depends on the alignment of magnetic moments with or without the applied external field. Three types of magnetism is observed depend in the different materials. Those are the diamagnetism, paramagnetism, and the ferromagnetism. So we'll discuss each one clearly. So what is diamagnetism? So diamagnetism arises in the materials due to the orbital motion of the electron. Due to the change in the orbital motion of the electrons, this diamagnetism will comes when there is the application of the externally applied field. If you apply the externally applied field, this externally applied field H will impose some force on the electrons, which will changes its angular momentum and changes its velocity of the electrons which are moving in the orbitals around the nucleus. Due to that change in the orbital motion of electrons, the magnetic field, this magnetism will come and is said to be the diamagnetism. Here we'll read this weak form of magnetism which arises only when an external field is applied. Before applying the external field, these diamagnetic materials are like non-magnets. When you apply the externally applied field, the magnetic moments, these due to the change in the orbital motion of electrons, the magnetic moments arises and the magnetism will develop. So it arises due to the change in the orbital motion of electrons on application of the magnetic field. As I already told, by applying the externally applied field will affect the orbital motion of electrons due to the force of the externally applied field changes the velocity and the angular momentum and produces the magnetic moments. So there is no magnetic dipoles in the absence of the magnetic field. As seen in the diagram here, before applying the external field, that is H is equal to 0, there is no dipoles here. Dipoles are not present before applying the externally applied field. When a magnetic field is applied, the dipole moments are aligned opposite to the field direction. In this type of materials, the dipoles will align opposite to the external field. So here we can observe that all the dipoles are aligned opposite to the direction of the external applied field. And here examples are Al2O3, copper, gold, and silicon and the zinc. These are all the examples for the diamagnetic materials. In the diamagnetic materials, magnetism will develop exactly in opposite to the externally applied field, and these diamagnetic materials are having a wide variety of applications. Mainly these are used as a protective coatings on the sensitive circuits. So by using this, the magnetic lines of force will be aligned opposite in direction to the external field, which will avoid the electromagnetic interference. So to to protect from these electromagnetic interactions from the circuitry devices, we can use these diamagnetic materials as the protective coatings or protective shieldings. And we will summarize the diamagnetic material features of the diamagnetic materials. So the diamagnetic materials are substances which when placed in a external magnetic field develops a weak magnetism in opposite direction to the externally magnetic field, and the atoms have very small magnetic moment, and the slightly repels the magnetic lines of force. So here the magnetic lines of force which are applying externally will repels the by the magnet. And the examples are bismuth, silver, copper, and the hydrogen. The relative permeability of the materials slightly less than 1. As I already told, these are the weak magnets. A weak form of magnetism is observed here, which is represented by the permeability that is less than or equal to less than 1. For example, the relative permeability of the bismuth is this value, that is 0.00083, and copper is very less, that is this much value, and wood is this. So these are the examples of the relative permeability of the different materials. The diamagnetic susceptibility is very small and negative, that is equal to less than 0. It is due to the repulsion experienced by the diamagnetic materials when placed in a magnetic field. As I already told, these materials are repels the externally applied magnetic field in exactly in opposite direction. So due to that, the susceptibility value is very small and negative. And next one is the paramagnetism. As I already discussed in the previous slide, the main reason for the diamagnetism is the change in the orbital motion of the electrons by the application of the externally applied field. So the next one is the paramagnetism. This is due to the uncancellation of the in this uncancellation of the magnetic moments is the main reason for the paramagnetism. Here in this, the cancellation of the magnetic moments between the electron pairs is incomplete. So the electron pairs magnetic moments are not cancelled completely. There is a finite magnetic moments will be remained in the materials. So hence magnetic moments exist without any external magnetic fields. So here we can see this here. Here there is a random alignment of the dipoles. So due to that, there is a uncancelled magnetic moment is observed in the absence of the externally applied field. However, the magnetic moments are randomly aligned, hence no net magnetization. So these are all randomly arranged. So there is no net magnetization without any external field. So before applying the field, these are all like non-magnets. When you apply the magnetic field, the dipoles, which are the dipole moments which are present in the material, will align perfectly into the direction of the field and will produce the finite magnetic moment due to the alignment of the dipoles into the direction of the externally applied field. So examples are Al, aluminium, chromium, molybdenum, titanium, and the zirconium. These are the examples for the paramagnetic materials. For the paramagnetic materials, the magnetic susceptibility is very small, and but this is value is positive because these magnetic dipoles are aligning in the direction of the field, so susceptibility value is positive, but it's a less value. P in a paramagnetic magnetic material is slightly greater than that of the vacuum. So for the diamagnetic materials, B value is less than the vacuum. For the paramagnetic materials, the B is slightly more than the vacuum. So this is about the summary of the different susceptibility values for the diamagnetic and the paramagnetic materials. Here we can observe that the aluminum oxide is having the high susceptibility values, that is minus 1.81 into 10 power minus 5. And here different material susceptibility values are given, that is copper, gold, mercury, silicon, silver, and the sodium chloride and zinc. So if you come to the paramagnetic materials, here the sodium is having less susceptibility value, and aluminum is having the more value. Here the different materials like titanium, zirconium, all the values are mentioned here to observe the changes in the susceptibility values with the changes in the materials, and due to the alignment of the magnetic moments. So here diamagnetic and the paramagnetic materials are the non-magnetic because they exhibit the magnetization only when the presence of the external field. Only for these materials the magnetization is observed in the presence of the external field. So these are considered as the non-magnets. So if you observe the graph between the field density, that is induction B, and the magnetic field strength H, we can observe that if the magnetic field strength is increasing slowly, then the flux density also increases, and this flux density is a lower value than vacuum for the diamagnetic, and it is slightly higher value for the paramagnetic. So if you increase the H value slowly, the flux density also increases for paramagnetic, and it is slightly lower than the vacuum only for the diamagnetic. And these are the features of the paramagnetic materials. We'll discuss here one by one. Paramagnetic materials are the substances which, when are placed in a magnetic field, develops a feeble magnetism in the direction of the magnetic field. When you keep these type of paramagnetic materials in the external applied field, then the magnetic field will develops. The atoms are slightly oriented along the direction of the external magnetic field. They attract the lines of force slightly. The examples are aluminum, tin, and the tin and magnesium. These are all the examples for the paramagnetic materials. The relative permeability is slightly greater than 1, and the susceptibility relative permeability example, the relative permeability of the aluminum is this much value, and the paramagnetic susceptibility is less than 1 but positive, because these are making the alignment in the direction of the applied field. That is here it is due to the it is less than 1, it is very small, but it is positive value. It is due to the slight attraction of the magnetic field when placed in a magnetic field. So as I already told, the magnetic dipoles will align in the direction of the field. Susceptibility value is a positive, but it is a small value. And next one is the these above three are the main categories of the magnetism, that is dia, para, and the diaparamagnetisms. And third one is the ferromagnetism. So this is also important, which is observed in the most of the ferrous materials. So that is certain materials possess the permanent magnetic moments in the absence of an externally magnetic field. This is known as the ferromagnetism. In the absence of magnetic fields also, some magnetic moments will present in the material in the area of the domains. Here these are all represented with yellow, blue, red, and green. These partitions are said to be the domains having a particular random orientation of the moments, but net magnetic momentum will exist in the ferromagnetic materials in the absence of the external field also. Permanent magnetic moments arise due to the uncancelled electron spins by virtue of the electron structure. So due to the uncancelled electron spins presence due to the unpaired electrons in the material produces the ferromagnetism. So this is also said to be the permanent magnets. So here the coupling interactions of electron spins of adjacent atoms cause alignments of moments with one another. So the interactions between the electron spins of the adjacent atoms. So here when there is interaction between the two atoms, then the spins will align and produces the magnetic moments. The origin of this coupling is attributed to the electron structure. So due to the electron structure, due to the alignment of the electron spins with the neighboring atoms will produces the finite magnetic moment, that is said to be the ferromagnetism. And we will see the features of the ferromagnetic materials. Ferromagnetic materials are the metallic crystals which, when placed in the externally magnetic field, becomes strongly magnetized in the direction of the field. These materials are strongly attracted by the magnetic field. These materials are strongly oriented along the direction of the externally magnetic field due to the presence of the permanent dipoles. They attract lines of force strongly. The examples are iron, steel, nickel, and the cobalt, etc. The relative permeability is greater than 1, and the example is here the purified iron and the many magnetic alloys having the relative permeability having this value very high value, and the ferromagnetic susceptibility is greater than 1, and also the greater than 1 is positive. It due to the large attraction, strong attraction between the dipoles and the externally field. And above the Curie temperature, ferromagnetic materials behaves as the paramagnetic materials. Their susceptibility is given by the Curie-Weiss law, defined as susceptibility psi is equal to here Curie temperature, here C upon T minus Tc, where C is the material constant, T is the temperature, and Tc are the Curie temperatures. So Curie temperature is nothing but where the material changes its magnetism from ferro to para to ferro or ferro to para. That limit is said to be the Curie temperature. So at the Curie temperature, susceptibility can be written as C upon T minus Tc. C is a material constant, T is the temperature, and Tc is the Curie temperatures. So this is about the brief differences between these diamagnetic, paramagnetic, and the ferromagnetic. So we will understand these 8 points. That is, first point is behavior in a externally applied magnetic field. So as we already know, develops the weak magnetism in opposite direction, and in paramagnetic materials develops the weak magnetism in the same direction, same here as shown in the diagram, below diagram, and also develops a strong magnetism in the same direction as shown here. All dipoles are aligned in the direction of the field. Here the second one is alignment of magnetic dipoles in the externally magnetic field. So here these all dipoles are aligned in the diamagnetic material opposite to the externally field. In the paramagnetic materials, these dipoles are aligned in the direction of the field. In the ferromagnetic, these are strongly aligned in the direction of the field due to the attraction between the strong attraction between the applied field with the ferromagnetic materials. And response to the external field slightly repelled by the externally magnetic field due to the uh, opposite alignment of the dipoles, and slightly attracted by the externally magnetic field. And the third one is strongly attracted by the externally magnetic field. And these are all the relative permeability values for the diamagnetic, paramagnetic, and the ferromagnetic. For the diamagnetic, that is less than 1. For the paramagnetic, that is greater than 1. For ferromagnetic, that is greater than equal 1. Susceptibility values are small and negative for the diamagnetic. It is less than 1 but positive for the paramagnetic. It is very high for the ferromagnetic materials. Effect of temperature. Susceptibility is independent of temperature, means ease of magnetism is independent of temperature. It obeys the Curie's law, means it depends on the temperature. Susceptibility decreases with temperature in the complex way. Here Curie point where the phase transition occurs, that is no Curie point for this dia and para, have a definite Curie point which obeys the Curie-Weiss law for the ferromagnetic materials. Hysteresis means when there is a change in the magnetism in the reverse direction, we can observe a hysteresis, means change in the magnetization. It follows the different way while it is reversing the direction of the magnetic field. That is not exhibited by the para and ferro. It is exhibited by the para and diamagnetic and ferromagnetic materials exhibits the hysteresis behavior while reversing the magnetic field. And more two different magnetic materials are the magnetisms are there. Those are antiferromagnetism. So if the coupling of electron spins results in anti-parallel alignment, the spins cancel each other and no net magnetic moment will arise. So as I already told, the interaction between the neighboring electrons, that is coupling of electron spins, results produces the anti-parallel alignment as shown in the diagram. So due to that, then spins cancel each other and there will be no net magnetic moment will arise. So due to the coupling of the electron spins, there is the cancellation of the magnetic moment between the parallel and the anti-parallel spins. So due to that, there will be no magnetic moment will arise. This is known as the antiferromagnetism, which is observed in the MnO, manganese oxide. And in manganese oxide, O2 minus ions have no net magnetic moments, and the spin moments Mn2 plus ions are aligned antiparallel to each other in adjacent atoms. So in oxygen atoms we don't get magnetic moments, but in Mn2 plus ions are aligned antiparallel to each other in adjacent atoms. So this is about the antiferromagnetism. And next one is last one is the ferrimagnetism. So this ferrimagnetism is observed in the certain ionic solids having a general structure of MFe2O4. M is any metal, shows the permanent magnetism termed as the ferrimagnetism. Due to the partial cancellation of the spin moments, we can observe a different types of magnetism is said to be the ferrimagnetism. Here we can observe from this diagram also. This yellow color represents Fe3 plus having tetrahedral structure of in A site Fe2 plus, that is octahedral structure, and Fe3 plus which is having the octahedral B site. If you observe this diagram, Fe3 plus in octahedral lattice site and tetrahedral lattice site will cancel and complete cancellation is observed. But in Fe2 plus, due to the presence of the net magnetic moment, we will observe a net magnetic moment due to the presence of the dipoles in the octahedral lattice site. So this type of magnetism is said to by the ferrimagnetism. And last one is the magnetic hysteresis. So we will observe that the behavior of the magnetic materials when you reverse the magnetic field after reaching to the saturation point. So here, if the field is reduced from the saturation by the magnetic reversal, a hysteresis develops. Means, if you are increasing slowly magnetic field, we will reach a saturation point A. And if you decrease the magnetic field strength, then the material uh, will follow a different path than to the initial path that is said to be the hysteresis. So as the field is reversed favorably, oriented domains tend to align in the new direction. Then when you are decreasing or when you are reversing the magnetic field strength, then the alignment of the magnetic domains will changes. They will align into the new direction. So they we can observe the hysteresis behavior in the materials. When H reaches to the 0 point, the point R, some of the domains still remains aligned in the previous direction, giving rise to the residual magnetism, said to the retentivity or remanence. So when you H reaches to the 0, then we can observe that a finite magnetic moment will still remain due to the alignment of the domains, that is said to be the residual magnetism, and also said to be the remanence, or in this diagram retentivity. So here the reverse field strength Hc at which the magnetization is 0 called the coercivity. So the negative field, the reverse field where the magnetization will become 0 is said to be the coercivity. And here, due to the hysteresis behavior, some energy will lost in the materials in the form of heat. They will follow a new path while reversing the magnetic field. Due to that, some energy is lost in the form of the heat. And we can observe there are the two types of magnets depends on hysteresis. We can divide the magnets into the two types. Those are the soft magnets and the hard magnets. So soft magnets are having low hysteresis, small hysteresis curve, and the hard magnets are having the big, means wide hysteresis curve. Here we can understand the differences from this table. That is, materials which retain their magnetism and are difficult to demagnetize are called the hard magnets. As I already told, so these hard magnets, they will retain the magnetism for longer time. It will take time to demagnetize. Those are said to be the hard magnetic materials. Soft magnetic materials are easy to magnetize and the demagnetize, and these materials are retain their magnetism even after the removal of the applied field, and these are said to be the making the permanent magnets. These hard materials will remain some magnetism due to the alignment of the magnetic moments. So these are used as to making the permanent magnets. These materials are used for making the temporary magnets. Those are the soft magnets. They have the large hysteresis loss due to the large hysteresis loop area. So the this is said to be the loop area for the hard magnetic materials. This is large for the hard, and this is small for the soft materials. And susceptibility values and the permeability values are low. Susceptibility and the permeability values are high for the soft materials. And coercivity and retentivity values are large because they can retain the magnetism even in the absence of the external field. And coercivity retentivity values are less for the soft materials, reverse condition for the hard one. And magnetic energy stored is high. And since have low retentivity and coercivity, these are not used for making the permanent magnets. Here the magnetism storage is less for the soft material, so those are not used for the preparing the permanent magnets. They possess the high value of the B and H product. Magnetic energy stored is less, as I already told. The eddy current loss is high because the loop area is high. For the hysteresis area is high, which represents the loss of the in the form of heat, that is eddy current loss is high. The eddy current loss is less because of the high resistivity. These are having the high resistive materials, so the eddy current losses are less. So these are about the soft and the hard magnetic materials, depends on the hysteresis curve. In the next video lecture, we will discuss the applications of the magnetic materials. Thank you, and thank you so much.